Hello, everyone. So thank you for attending this talk. This is Thibaut. I'm Valentin. We are both working at Capgemini Invent, which is a consulting company. Today we're going to talk about uncertainty, quantification, and how you can measure uncertainty using a powerful framework called conformal predictions. And then we'll deep dive into MAPIE, which is an open source tool that implements conformal predictions. We'll see a practical use case, and we'll have time for questions at the end. So why measuring uncertainty for AI practitioners or data practitioners like us is important? Let's take a simple example. Let's say we have a system that shoots an arrow, and we have a model that will try to predict where the arrow will fall. Here we see that there is a risk involved. We don't want to shoot that poor boy's head. So we want to be pretty sure that if shooting the arrow, we will not hit the head, right? But here the model just gives us a point prediction. Thanks to prediction intervals, which is a way of measuring uncertainty, you can now have two scenarios. The first one is there is a high confidence that the arrow will fall into this interval, which is actually an area. And we're pretty sure that we can shoot the arrow without any risk. Then we have the second scenario where maybe we should, call the human and say, should we shoot or should we not? Of course, this is a very simple example here, but you can apply this to critical systems in real-world scenarios, such as autonomous vehicles, medical treatments, and so on. There are many ways of predicting, measuring uncertainty. A lot of those ways may have maybe, for example, computationally tough, or you may need to have strong assumptions on your data. And Thibaut will show you that conformal prediction is a good framework because we don't carry those we don't carry the burden of those drawbacks.
Yes, thank you for this introduction. Definitively, we are very interesting to implement conformal predictions, and we have a good reasons to think about that. So why using conformal predictions? First, it's a framework for uncertainty quantification that produce a prediction set with good properties. Which ones? First of all, conformal predictions allow us to produce prediction sets that are associated with confidence level. And this is very important when we need meaningful interpretation. So just to give you some mathematics, so just here to see that, to say that when you see a new observation, what we would like to state is that this observation will be contained in our prediction set with high probability that is controlled with a small margin. And this is very important. And with conformal predictions, we can do that with few assumptions. First of all, we can do that without requiring distribution assumptions. So it is very strong. We don't need to use normal assumptions. It's still working. We only require exchangeability data assumption. So it's less than AID assumption. And finally, and I think it is the most important one, it's still agnostic to model and use cases. So if we would like to use it for NLP use cases, computer vision, for time series, if you have your own data set or your own model, for example, a linear regression or a deep neural network, it's still working. And just to be short on how it works, it's these properties are provided by the quanti-lemma, and I will just to give you some pictures on how the more standard split conformal predictions works. So first of all, you have the first step to train your model. So your model is just a point predictor model. It's important, but it's not enough to do uncertainty quantification. Okay, so we need to have a calibration step in order to build a set predictor model. So we split our data set into trained data and calibration data. When you do that, after, you need to define a non-conformity score. So what is a non-conformity score? It's just a function that quantifies how well an observation X is conformed with a target Y. So if this quantity is low, it's a good thing. It is higher, it's more atypical value. When you say that, so you just need to compute the non-conformity scores on your calibration data set. And because I'm talking about the quantile lemma, you just need to compute the quantile with desired confidence level with some correction to be sure that you cover your empirical non-conformity score distribution. So it's just an illustration on how it works. You just estimate this distribution, and because you compute this quantile, you are sure that for future observation, you will continue to control the non-conformity score distribution, and then what you need to do is just to keep all the target Y that verify that the non-conformity score is under your control quantile. That's all. And conformity score, conformal prediction is just that. So if you understand that, it's okay, you can just use it for any use cases. And just to conclude my presentation and to give you some insights on how it works on regression and classification, here we can see that for the same level of confidence level, we will produce different intervals which contain different values considered highly probable. So if this interval is small, we can state that they are low uncertainty, so we expected a low error, and then we can say that I know that the model knows. And it is important for us. In the opposite case, we can see sometimes we have large intervals, so we have a high uncertainty. We can expect high error, but it's not a problem here. It's not a problem because we have still the information that the model doesn't know. And we can imagine, with the examples that Valentin presents before, different scenarios on which we will talk to human to give the expected answer, for example. For classification, it's quite the same thing, but here we don't talk about interval set, but we will talk about prediction set. So it's just a subset of classes on which we trust the true label is inside. So on the left, we are a low uncertainty because we only return one class. So I'm pretty sure that it is a Fox square. But in the opposite side, if you hesitate between different classes, you will return a subset with different classes with close scores. And so in this situation, you know that the model doesn't know. That's all. And I will just let Valentin to present how we implement this in MAPIE.
Thank you, Thibaut. So now let's dive into MAPIE. So MAPIE is an open source tool that allows you, as you know, may have understood, compute prediction sets. It's pretty easy to use and good to know it's use case and model agnostic. It's fully compatible with scikit-learn, and you can also use it with, let's say, more exotic models. It's pretty easy to just wrap your models and use MAPIE, even if they're like pretty weird ones. We talk a lot about uncertainty, quantification, and conformal predictions, but because that's the history of MAPIE. But we also are implementing tools from the more broader theory that is the risk control theory, and we plan to do more of this in the future, because that's where lies the true power of MAPIE and where we can really address complex business issues. And finally, again, we're providing statistical guarantees on what you're doing. So just a quick look at the code. It's pretty simple here. You can install MAPIE using Conda or pip. And then a very simple example, a regression example. So we're just fitting a linear regression. And then to use MAPIE, you just have to import that MAPIE regressor class and wrap your model. Then you will need a calibration data set to, well, calibrate that model. And then at inference time, for every new observation, you will get your prediction point, but you will also get a prediction interval. So on the right, you can see different prediction intervals for different level of alpha, which is basically your risk level. You can, of course, do the same for classification. The code is pretty much identical. And here, if we focus on the chart on the right, the colored areas are basically the zones where the model will predict sets that contains only one class. So it means that the model is pretty sure of what it's doing. On the other hand, the gray zone represents the area where the model will either predict empty sets or sets with more than one class, meaning that the model here is less certain or maybe very uncertain about the true value. So of course, what I just show are very basic examples, but we implement a lot of tools related to conformal predictions, and we try to stick as much as possible to what is published in the scientific literature. So we implement only things that we saw in papers. And I will let the floor to Thibaut.
Thank you, Valentin. And because I'm talking about earlier about use cases, I would like to go deeper in one particular use cases. You can decline as well for your own use cases. So it's a quite complex one, but it's just an example to give you the full pictures of all the possibilities you can have with conformal predictions. So imagine that you have a conversational agent and you would like to do some selective classification. So this agent is deployed on a robot and you would like to ask to the robot to give you some instructions. Here, we would like to ask to the robot to place a ball in the microwave, please. And so, because the robot needs to process the observations, the pictures, the context on the environment, etc., we can just imagine that the robot have the possibility to choose different actions. Here, we can see that he can put plastic balls in microwave, he can put metal ball in microwave, or he can put a metal ball in landfill bin, etc., etc. So all the possibilities because he sees that in its environment. So in the picture, I don't know if you can see that, but we can see there are two different balls on the table. Here are how do you say that? A confusion between which ball the user is talking about. And so to avoid misunderstanding, what we would like to do is that the AI agent asks for clarification when it is unsure about the action to take. So here, because we will use conformity scores, he will hesitate between the two first actions, so put the plastic ball or put the metal ball. And the only elements that we care about is the size of the prediction set. Definitively, because if we set up our conformal predictions with a confidence level or 95%, I'm pretty sure that if the agent return me a prediction set with a singleton, I have a low risk of misunderstanding. And so I can trust the robot to automatically apply its action. In the opposite case, in fact, if I can see that the prediction set size is at least 2, is for me a sign that there are a high risk of misunderstanding. And so in this situation, I will prefer that the system ask for help before to apply an action, before to perform an action. So just to be give a short story about this use case, the goal is to ensure that the model acts safely in 95% of cases. So you have the choice to do it by himself or to ask for clarification. So just to illustrate this with MAPIE, we will just propose to have conversational agent and to apply MAPIE only on this part of the huge solution. And because Valentin explained that before, we can use any models with MAPIE. And in this example, I'll propose you to use a custom MAPIE wrapper that we can define anyone in this room to wrap your models. So here, I propose to use a transformer model in the Huggins Face package. And what you just need to do is just to adapt the fit predict routine with the scikit-learn API. So you just need that because each models are have its own specificities, its own complex data structure. You need just to be sure that the API is still compatible with scikit-learn. Then is very easy just to use the routine by wrapping your pipeline with your wrapper, then use your non-conformity score and conformalize it with the MAPIE classifier class. And that's all. You just need sometimes some hyperparameters if you want, because we propose different strategies, but that's all. You just need to use the predict methods, and you will have a prediction point and a prediction sets. That's all. I would like to propose you a notebooks, but I will give you the time to do in your side. So you can see that on the GitHub on MAPIE tutorial, or directly on the MAPIE package. You are free to check that by yourself. But it's only the same snippet code I presented you just before. And just to conclude, to give you some results on what we can produce, here I propose to build a prediction set with a confidence level of 80%, and I can see that I will produce different prediction set size. Almost 60% are equal to 1, and almost 80% are smaller than 3. So we can have some interpretation on which actions my agent is confusing. If I take this example here, how do you prepare a taco? In fact, the initial answer of my model is to return cook time. But in fact, the true label is receipt. If I trust the model, perhaps the model will do harmful action. But because I can have access to the prediction set, I can see that I have 4 different suggestions. And so instead to let my agents alone, I will allow him to ask me for clarification. And I will just let Valentin to conclude this presentation.
Yes, so just a few words to sorry, to wrap this up. So MAPIE is an open source project. We also have comprehensive documentation, of course, for users that explains how to use MAPIE and how to get started. We also have a more, let's say, scientific documentation if you want to get started on understanding conformal predictions. We do publish scientific papers, and of course, we're actively maintaining the library. A quick look on the roadmap. So we want to land pretty soon on a version 1 with an improved. We want to find like there is no best, but a very good API for you to use MAPIE. And we also want to revamp the documentation, so the overall architecture of the documentation is very clear, and we want to focus on practical use case. Another thing we want to explore is the scientific literature about large language models and conformal prediction. And so we plan to, if we find it relevant, implement stuff related to that in the future. And then, as I mentioned before, we want to address the use case of risk control and also implement tools for hypothesis testing. Of course, this is very open to suggestions. We are able to do all of this first because of a pretty large team internally, but also thanks to partners. Of course, we're backed by Capgemini Invent, but we also have external partners, and also thanks to a lot of contributors. So thank you, everyone, for this, and thanks to our partners. And so just to take a step back before finishing the talk and going through questions, MAPIE is just part of a broader framework, let's say, that is reliable AI. And that is pretty important, and as you may know, for example, the AI Act is getting legally grounded, let's say. In reliable AI, you also have explainability issues, the frugality topic, for example, so you have all those topics that you may want to address. Regarding data quality, we're actually also developing and maintaining another open source library, so you may want to check it out. It's called Colmat, and the goal is to help you input missing data points. So that's it for the talk. Thank you for your attention, and we can proceed to questions if you have.
Thanks for the very nice talk. I have two questions, sorry. The first is, do you have some business wisdom on how to select alpha? I guess everybody wants alpha to be 0, but that leads to a useless prediction set. And the second is, how do you see MAPIE differentiate itself from the package called conformal prediction from Angelopoulos?
Okay, so for you hear me? Okay, perfect. So yes, for the first question, you are totally right. It's just a question of business insight. So if you use alpha equal to 0, you will produce infinite prediction sets. That's not interpretable, it's useful. So yes, it's just a trade-off to have. It just depends on the level of risk you would like to have. Yes, it depends. And we don't have a satisfied answer. And for the last question, I just have difficulty to hear you.
Yeah,
Can you
sorry.
repeat, please?
Can you hear me better now? Yeah, I think it's better. So there's another package for conformal prediction, which is called conformal prediction, by the Berkeley researcher Angelopoulos, which I think you mentioned as one of his researchers. How do you see MAPIE being different or complementary to the existing conformal prediction package?
Okay. In fact, for our point of view, we just propose a solution that is scikit-learn compatible. So for our case, we just propose for anyone that would like to use it to do this easily. So there are not a conflict with other package. So if I would like just an advice, it's still a choice of any users. If you prefer one package or another one, it's up to you. It depends on your use cases, because also sometimes it depends on which guarantees you want to have. Yeah.
Thank you for the talk. What are your recommendations for the calibration dataset? Should it be done on the testing dataset, the evaluation one, a combination of both, the training? What are your recommendations on that?
Yeah, so the calibration dataset is part of like the data you know before testing. So it's part of that dataset that you split between train and calibrate. It's the same when you're doing cross validations and things like that. And so regarding the size, I think the default is 20% of the entire training set, but you can adjust that. Basically, a too small calibration data set will tend to output larger prediction sets. So it's getting less useful, basically.
Hi. Yeah, thank you for your great talk. I had a question about what you have in mind for the future. So I think you mentioned like a few improvements on the package, and also, do you have in mind to implement like the common improvements that there is in the literature? For example, I think you heard about cross-conformal prediction. I think it's called, like about splitting the training set into folds in order to, like for example, if you lack some data and you can't afford to isolate a calibration set. So, well, I think you know about it, but is it in your mind, or just like, do you plan to make a wrapper that facilitates all that operations? Or?
Yes, that's a very good question, and actually we're already implementing cross-conformal prediction. As I said, the examples we show were like basic ones to get started, but we're doing jackknife, CV+, and things like that, if you know the theory, and that's already implemented. But we're super open to know which algorithm you would like to, or which tool you would like to be implemented next, because that you are the user, so that's very valuable to us.
So one last question.
Thank you very much for the talk. I just wanted to know what's the level of degradation of performance of conformal prediction, because I assume when you have multiple label predicted instead of one, you can have a small drop or a big drop. What's the level in your experience?
If I understand well, our question is plus a question of adaptivity with local noise or not. This is your question?
Local modes.
Local model? Local noise. Ah, local noise. Okay, perfect. So I will take these questions, okay? And so, yeah, definitively, in the standard framework, we just control your residuals in a global point of view. You just guarantee the marginal coverage. And definitively, in the scientific research, they try to find more and more adaptive solutions to capture local noise, and so to be more performant with the heteroscedasticity of your dataset. And so currently we propose two main solutions. The first one is the conformalized quantile regression. So it's very performant because you use all the benefits of quantile regression. And we also propose the Mondrian conformal predictions that also allow you to guarantee the coverage inside your subgroups. So it's up to you to define it. It's business insights. So yeah, definitely, yeah, such solutions. And in the roadmap, we continue to add more and more adaptive solutions. So I hope that I answer your questions.
And so maybe if the question was related to a drop of in performance of the original model, let's say, basically we're not modifying that model. The only drop you can observe is because you train the model on less data. And actually there are methods where you try to minimize, of course, the amount of data you use to calibrate. But basically you will not see any drop, except the fact that you have less data to train the model on.
Thanks. Please give them another round of applause.